In this video, I'll talk through the Advanced Higher Chemistry Unit 1 Transition Metals topic. At the end of this video, you should be able to describe the electronic configurations of the transition metal atoms and ions, be able to calculate oxidation numbers and use them in the context of redox reactions, be able to name transition metal complexes, explain the colour of those transition metal complexes, and explain why transition metals are able to act as catalysts. The definition we will be working with at Advanced Higher Chemistry is that transition metals have an incomplete d subshell in at least one of their ions. We still fill the orbitals using Aufbau's principle. When an ion is forming, the transition metals will lose the 4s electrons before the 3d electrons, similar to what we talked about before. Because the electronic configurations of the transition metals can be quite long, we use the closest noble gas, which is argon, to represent up to 3p, and then we add in the other orbitals that represent the particular transition metal. If we're dealing with something like iron has 26 electrons. If we get up to argon, that takes us to 18 electrons, and then it'll be 4s2, 3d6. Similar to all the other ones we've done before, 4s is filled before 3d. When it comes to losing electrons, 4s is lost before the 3d electrons. When we have iron 2+, we have lost the two 4s electrons, and that leaves you with a configuration of argon and then 3d6. If it was the full thing, it would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d6 for the iron one there. If we were looking at iron 3+, we would now lose one of the electrons from the 3d subshell, and that would leave us with 3d5. Moving on to two chemicals which do not fall into the category of transition metals using the definition about unpaired electrons in ions. If we have scandium has 21 electrons, and this is its base ground configuration. If it typically makes 3+ ions, it's going to lose both of the 4s electrons as well as the only 3d electron that's present, and that will leave it with the same configuration as argon. It does not have an incomplete d subshell. It has an empty d subshell, therefore it does not fit the definition of transition metal. On the other side of the table, we have zinc, which has 30 electrons. Base configuration 4s2, 3d10. Typically forms 2+ ions, meaning it would lose both of the 4s electrons. We now have a situation where we have a full 3d subshell. That is not an incomplete one, and it doesn't tick the box for our transition metal definition. Those were the two ones that don't quite fit that particular definition. Moving on to the uses or what transition metals can do. They can form complexes where the metal gets surrounded by chemicals described as being ligands. A ligand is a chemical which is able to donate a pair of electrons to the metal ion. They form a special type of bond called dative or coordinate bond. In these ones, both of the electrons have came from the ligand to form the bond, whereas in more typical bonding, each chemical would bring an electron each, and that would form your normal covalent bond. So dative or coordinate, both of those words are used interchangeably in these kind of questions. Ligands can be classified in terms of how many bonds they can form with the metal. You have monodentate ligands, which form one bond to the metal ion. Mono for one, dentate is talking about tooth, because it can make one connection to the metal, described as monodentate. Any chemicals that can form more than one bond would be described as being polydentate. There are specific words for specific numbers of bonds they can make. We have bidentate for 2, tridentate for 3, tetradentate for 4, pentadentate for 5, and hexadentate for 6 electrons being bonded to that metal. Ligands such as cyanide, water, ammonia, and the halogens will all be able to donate one electron pair and are described as being monodentate. Quite typical ones to have in questions. Oxalate, coming from oxalic acid, is another one. This one binds twice, so bidentate. And then ethylene diamine tetraacetic acid, more commonly described as being EDTA, is hexadentate. It will make 6 bonds to a metal ion. These are your typical ligands that will come up in a lot of the questions. The names in the complex get tweaked. Aqua instead of water. IDO is quite a common ending for them as well. Amine, we've got two M's in amine. That is not a misspelling. It's different to the carbon chemistry amines that you've dealt with. This one is acting as a ligand, so it's AMMINE. And then you have your cyanido, hydroxido, and oxalato for the oxalate one there. Coming to the formulas, water is written as OH2. This is because the oxygen is what has the lone pairs which allow it to bond to the metal ion, and that's why we write it as OH2 instead of H2O. And you have your different charges as well, what you need to be aware of. When it comes to describing things called oxidation state, this is looking at its oxidation number, and this is very much linked to the charge on that particular element or substance. If we have iron 2+, in this iron chloride compound, it will have an oxidation state of +2. Typically, when we talk about charges, you do the number and then the plus or minus, so 2+. In an oxidation state, it's more typical to write it the other way around, so +2 for your oxidation state of iron in the first one, and then it's now +3 for the iron 3+ chloride. If you're asked to figure out what the oxidation number is, there are certain steps that you can take. First thing is if it's an uncombined element, it'll just be 0. So something like oxygen and oxygen gas or metallic sodium would both have an oxidation number of 0. If you have a single atom ion, it will be the same as the charge on that ion. Magnesium 2+ +2, and iodine 1- would be -1 as its oxidation number. Usually oxygen will be 2+, hydrogen would be 1+. There are exceptions in things like peroxides and metal hydrides where the values are different. Most of the time though, it will be -2 and +1 for each of those. If you have a neutral compound, all of the values must add up to 0. Something like calcium carbonate, where calcium is 2+ and carbonate is 2-. They cancel each other out, and that gives you a neutral compound. If you have a polyatomic ion, that's the ones that you find on page 9 of the data booklet. These ones show the overall value that came as a result of the different atoms that are present within it. So for example, if you have carbon is going to be 4+. Each oxygen, because it's O2-. If you have 3 of them, that gives you a total of 6-. 4+ and 6- leaves you with 2- overall. And that's how those ones come about. You can use the data booklet to help guide you when needed. If you have something like hydroxide has an oxygen which is 2-, a hydrogen which is 1+. Put them together gives you 1- overall, OH- for hydroxide ions. Transition metals can exist with different oxidation states, which allows them to have a wide range of uses and applications. One of the most common oxidation states is +2, which happens when they lose their 2,4s electrons. Different oxidation states can result in different colours being shown by those complexes. Here are just a couple of examples from compound interest, where things like vanadium have a wide range of different oxidation states, and then that allows them to show different colours of those. You might have done an experiment where you take one of the transition metal complexes, you react it with something which changes the oxidation state, and you have a nice broad spectrum of colours as it transitions through each of the different states. Getting to an exam style question, you may be asked to work out what the oxidation number is of a particular metal in a particular compound or complex. In this one, we have oxygen being joined to vanadium. Oxygen will have an oxidation state of -2, and if you've got 2 of them, that means you have -4 combined together. Because there is no charge showing on the VO2, the vanadium must balance out the -4. It must be +4, give you a neutral charge overall, and that gives you your answer of +4. You can represent it with Roman numerals or just as a singular number. Those would be acceptable to the SQA. Moving on to the next one here, they are asking you for the arrangement of sp-d orbitals for nickel in this complex. First thing I would do is look and see about the ligands. Water is a neutral ligand. That means that the 2 plus outside the square brackets must have came from the nickel. So we have nickel 2 plus. Nickel has 28 electrons. My recommended way to do this is write out the full arrangement for the 28 electrons. And that gives you 1s2, 2s2, 2s6, 3s2, 3p6, 4s2, 3d8. Next, we are losing 2 electrons to become +2, and we are going to lose the 4s electrons before the 3d electrons, and that leaves you with the 1s2, 2s2, 2s6, 3s2, 3d6, 3d8. What I don't want you to do is to remove the 2 electrons before writing it out. If you remove the 2 electrons first, you would end up with nickel being 4s2, 3d6, which is incorrect. You need to be remembering that the 4s fills first, and the 4s is also lost first. When it's empty, it's at lower energy. Once it's occupied, that's the one that gets lost before the 3D, and that'll get you to the correct answer here. Next, we're going to just talk about coordination number related to the coordinate bonds / dative bonds that we talked about. The number of ligands that surrounds a transition metal can vary. The number of bonds from the ligands to the metal ion is known as the coordination number. How many coordinate bonds are being formed to the metal ion? In this one here, we have 6 waters. Each water joins once because it's monodentate. So there will be 6 bonds to the copper. That gives it a coordination number of 6. In this one here, we have each chlorine making 1 bond to the copper. That gives it a coordination number of 4. Different coordination numbers will result in different shapes of the molecules depending on what else we have present within it. And we have our typical shapes that we've had from before of linear, tetrahedral and octahedral. We could also get square planar depending on the number of lone pairs, etc. Shuffling on here, we are asked to classify this type of ligand. This type of question wants mono, bi, tri, tetra, penta, or hexa dente ligand. Key thing here is that there are 3 of the ligands. A couple ways I can show that is up in the formula, it talks about the fact that we've got 3 of those long ligands. You can also see here that there are 3 different things joined together. Each ligand joins on twice, therefore it's a bidente ligand. So we are looking at each of the individual ligands. So there are 3 ligands, but each of them makes 2. For the coordination number, it's just how many bonds are being made to the central atom. Each ligand was making 2. There are 3 ligands, so that makes it 6 pairs of electrons and a coordination number of 6. Type of ligand, each individual ligand molecule, coordination number in total, regardless of where they've came from, how many bonds are being made to the central atom. So we had our 6 for our coordination number there. When writing the formulas of the complex ions, we always put the metal first, negative ligands, and then neutral ligands, as shown here. Square brackets around the complex with the overall charge on the outside. When it comes to naming them, it should be written alphabetically if there are more than 1 ligands. We don't care about di, tri, etc., hexa. We just care about the name of the ligand. So aqua before clarido, and so on. Ide becomes ido, ite becomes ito. And a lot of questions will kind of guide you with these ones as well that you need to do. If the overall charge on the complex is positive, the name will just be as expected, copper, cobalt, titanium. If the overall charge on the complex is negative, the name will be changed. Cuprate, ferrite, cobaltate, chromate, vanadate, cuprate, and ferrite. Here, I'm going to try and name this chemical. We have got 6 water ligands. That's going to be written as hexa aqua. Overall, it's a positively charged complex. It says 2+. That means that the name of the metal will just be written as is. So it'll be hexa aqua copper. Water is neutral. That means that the 2+ on the outside must have came from the copper, which we write as Roman numerals in brackets. Hexa aqua copper 2 would be your final answer for that one. Here it's 4. It's chlorido, tetrachlorido. It's overall negatively charged, therefore it will be cobalt 8, tetra cobaltate. each chlorine will be 1 negative. This gives you 4 negative for the chloridos. To get to 2 negative overall, your cobalt has to be 2 plus. We'll put 2 in Roman numerals at the end of the name. Tetrachlorido, because there's 4 chlorines. Cobaltate, because it's overall negative and it's cobalt. And then the 2, because it has to be 2 plus on the CO to overall have 2 negative at end. Next one, we are working back the way. Here we've got 6 ammonias. So that will be NH3 in brackets with a 6. It's chromium. That means it's going to be Cr. So Cr, and then you've got your NH3, 6. It's going to be positive overall because it's chromium, not chromate. Amine is neutral. This means that the 2 negative on the outside must have came from the chromium, and that's why you get 2 plus outside of the brackets. That one. And then in this one here, we've got copper. It's overall negative because it says cuprate. Tetrachlorido means that there's going to be 4 chlorines, and the copper has got to be 2 plus because it's got a 2 in the brackets at the end of the name. So actually looking at it, very similar to the second one, just copper instead of cobalt, but it works out the same. Here is more of the exam style question. You have to state the name of this particular complex. We're dealing with 6 ammonias, so hexaamine, that's with 2 M's. We've got nickel, which is in a positive complex, so it's just nickel. It's got neutral ligands, therefore the 2 plus must be from the nickel. So putting that all together, hexaamine nickel brackets 2 gets your answer for that one. And here we're asked to do a negative complex this time. So this one would be hexafluorido cobaltate, because it's negative overall. Each fluorine is 1 negative. Therefore, your cobalt has got to be 3 plus. Then you've got 3 plus from CO, 6 negative from F6. Overall, 3 negative gets your answer. Just like that. In a question like this, they have got lots of different options and you have to pick the correct one. Something that will save you a bit of time is if you look inside the brackets, it's all identical inside the brackets. They are all tetraamine, dichloro, and it's got copper in there as well. This means you need to focus on the charge of these. Couple ways of ruling some out. It is not going to be A because A is 2 negative overall. If it was 2 negative overall, it would be cuprate, not copper. A is wrong for that one. Probably the better way to do it is to look at it and say, well, each chlorine is going to be 1 minus. This gives you 2 minus overall for the chlorine. It's copper 2, which tells me that it's 2 plus on here. If it's 2 plus, amine's been neutral. 2 plus and 2 minus gives you no charge overall, which means that B would be the correct representation of that. So a bit of a different way around to get to your answer, but that would end up with your answer of B for that one. In this one here, they're doing it as a diagram. You need to be able to figure out which ligands that we've got. We have got 1 NH3 and we've got 3 waters written as OH2 as explained earlier. Starting off with the naming of them, you want to do it in alphabetical order. So amine becomes before aqua. So we would have amine, penta, aqua for the ligands. Each of those is neutral, which means the 2 plus that you see on the outside must have came from the nickel, and that means you want brackets 2 at the end. Putting it together, amine, penta, aqua, nickel 2 would be your final answer for that one. Next we get to using the oxidation states to show if it's a reduction or an oxidation reaction. To do that, we want to look and see is there an increase in oxidation number, therefore it would be oxidation. A decrease in oxidation number would be a reduction reaction that we're having. Looking through this one, both of them have oxygen, and oxygen would have a 2 minus charge. In the first one, we have 6 negative from the oxygens, therefore it must be 4 plus on the sulfur to result in 2 negative overall charge. And then the sulfur in the second one must have a bigger charge, because there's 4 oxygens attached to that, and it's still 2 negative overall. We are increasing oxidation number, therefore this is an oxidation reaction. Depending on the question, you might find that page 13 has those chemicals in the electrochemical series. In this case, in the data booklet, it starts with the SO4 and ends in SO3, and that is a reduction reaction. Our one is the opposite way around, therefore it's got to be an oxidation reaction. Not all the questions will have them in the data booklet, so this way I've done it here works every time. You might have the data booklet there ready to help you for certain questions. In this one here, we've got our dichromate going to chromium 3+. Again, each oxygen will have 2 minus, 14 minus in the dichromate, first chemical. That means to get 2 negative overall, it has to be 12 plus from both in total from the chromiums. That means each chromium must be 6 positive to make that work. We're going from 6 positive to 3 positive. Its number's going down, therefore it is a reduction reaction. This one again is in the data booklet, so you could just use it there. It matches page 13, therefore it is a reduction reaction. A lot of the transition metal complexes will be colourful. This is because they will absorb light in the visible spectrum, and we see the complementary colour. We see the colours that are not absorbed. The colour wheel on page 19 of the data booklet can help you with that. If green's absorbed, that means that blue and red would be transmitted, and we would see purple. If red is absorbed, then we would see blue-green. And if blue is absorbed, we would see yellow. Colour wheel can be used to help guide us towards what is seen and what is absorbed. Now we'll go to look at why they are able to absorb light and appear as different colours. It's to do with the fact that in a free ion, the orbitals in the d subshell will be degenerate, equal energy. Those ligands will then create an electrostatic field around those, which cause the d orbitals to be split. And what ends up happening is we have 2 orbitals which are higher in energy and 3 orbitals which are lower in energy. The lower energy ones would fill first, and then once the lower orbitals are filled, then it would start filling the 2 that are of higher energy. The spectrochemical series shows which ones split more versus which ones split less. You don't need to know specifics of which ones split more or split less, but you have to be aware that some chemicals will cause a larger splitting than the other ones. If radiation of the correct energy is absorbed, an electron can be promoted from the lower d orbitals to the higher d orbitals, and this is what's described as being a d to d transition. If that light falls within the visible spectrum, you will see a colourful compound. In these examples here, the first one is absorbing mainly in the red region of the visible spectrum. This means that when red light is absorbed, we will see blue and green being transmitted, and this will appear as a blue-green colour compound. In the second one, it's more in the yellowy region of the spectrum. That means that you would have blue light being transmitted, yellow being the mixture of green and red. This chemical would then appear blue. Data booklet can help kind of simplify that a little bit. We had yellow resulting in blue, and then we had red resulting in blue-green. This topic then links back to the electromagnetic spectrum that you've done previously, where you have your red, orange, yellow, green, blue, indigo, and violet. You need to be aware that the colours towards the right-hand side, so that's your blues, indigos, and violets, will be of higher energy versus the ones on the left, which are of lower energy. Therefore, if the splitting is greater, electrons will need more energy to be promoted. This makes them more likely to absorb light in the blue, indigo, and violet regions, and then appearing as the complementary colours of those ones. If the ligand has got a large energy gap, this means that the chemical will likely absorb light in the UV range. This would then result in a colourless compound being observed, because shorter wavelengths will correspond to a higher energy gap. In this question, we're asked to explain why a particular solution would appear green. If a substance appears green, it will absorb the light that is opposite it in the colour wheel, which in this case would be purple. This is the light that would cause the d electrons to be promoted from the lower energy levels to the higher energy levels. lower d orbitals to the higher d orbitals. Purple light is absorbed, and this causes electrons to move to the higher d orbitals. Now, in this question, we are given two different complexes, and we're asked to explain which of them would have the greater ability to split the d orbitals. A greater ability to split would cause a larger energy gap, which would need a lower, smaller wavelength of light to be absorbed. If we look at these two, the one that absorbs at lower wavelengths would be the one with the ammonia, the dashed line. The NH3 causes shorter of wavelengths of light to be absorbed. This must mean that there is a higher energy gap, which means that that has the greater ability to split the orbitals. If you went the other way around, the water ligand causes a longer wavelength of light to be absorbed. Longer wavelength is shorter energy gap, so it's less split. Number 3 here, we're asked about why a particular solution is going to be colourless. And this one we need to catch that we're talking about zinc. And zinc was one of those two that didn't quite fit into the category of transition metals because as an ion, it has a full D subshell, whereas a transition metal needs an incomplete D subshell in at least one of its ions. Because it has a full D subshell, that's quite a stable arrangement. It will absorb ultraviolet light, not visible light, and that will result in a colourless solution being formed. Transition metals and their compounds can act as catalysts. There are two types of catalysis that we're going to focus on. That is heterogeneous catalyst, where the catalyst is in a different state to the reactant, versus homogeneous, where they're in the same state as each other. Catalysis involves making activated complexes and the reactive molecules adsorb into the surface of the catalyst. It's believed that the unpaired electrons are what allows these substances to act as catalysts, able to form alternative pathways, and these pathways are the ones that have lower activation energies, which allow the reaction to happen more readily. This diagram is trying to represent what happens during the catalysis. We have got reactants forming bonds with the catalyst. This weakens the internal bonds, the intramolecular bonds within the substance. Because they're fixed on the catalyst surface, this makes there be a more favourable angle of the collision. Once the reaction has happened, the products will then leave the catalyst and new reactants can combine to the active site and the process can continue until all the chemical has been used up. Catalysts can be poisoned. If an impurity gets onto the surface of the catalyst, it will block the active site and then the reactants cannot adsorb to the surface, and then the activity of the catalyst will decrease over time. If leaded petrol is used in cars with catalytic converters, this has the potential to poison the catalyst. This means that the harmful emissions that would be usually converted into less harmful emissions is unable to happen. And that's why the vast majority of petrol used in the UK will be leaded petrol. In order to get maximum efficiency, catalysts will often be regenerated by reacting them with a gas which will remove the impurities and allow the catalyst to function more quickly. If you have a catalyst that's poisoned by something like carbon, for example, if you react that with the oxygen in the air, this will form carbon dioxide and that will clean off any of the impurities from the surface of the catalyst, and then it can work much better. There's a questions you can get. One question that was given was different statements about hetero and homogeneous catalysts. The bit I find the most straightforward is thinking about the same state or different state. Homo, same state. Hetero, different state. That narrows us down quite significantly, so it can only be A or D. We do need unpaired D electrons to be able to form those bonds with the reactants. Would rule out this example here. When we're discussing adsorption, we are talking about something like a gas coming onto the surface of a solid catalyst. This would make it heterogeneous and not homogeneous, and that gives us the correct answer of A. Catalysts will need to be able to change oxidation state as they react, but that still leaves us with A as being the correct answer. That brings us to the end of the transition metals topic. Hopefully at this point you are much more comfortable with the electronic configurations, oxidation numbers, naming, transition metal complexes, talking about the colour in terms of D to D transitions, and also a bit about how transition metals act as catalysts. Thank you for watching. Goodbye.